then we will be able to share out the recording later on the YouTube channel as we've done previously. We've got the Google document Alan has been sending out to the Slack channel. I posted it as well in the Zoom chat for today. Encourage everybody to get on, sign up in there for attendance for today, participate with us in keeping notes inside the agenda document for today. We have Maxim from ComputeCanada, who is going to lead today's conversation. This was at least inspired from a presentation a few of us were able to hear about or participate in at a recent PERC 19's conversation. So we will go ahead and turn the time over to Maxim to take it from here.
All right, thank you. Can you all hear me fine?
Yep.
All right, good. So thank you for having me. I think Martin extended the invitation. So this is a talk, as I think Brian said, that I gave at PERC, and to give a bit of a twist at PERC, I did show that we could use the cluster stack that we have on ComputeCanada even on Windows. And before PERC, I did a quick Twitter poll about how people found that idea, whether it was crazy or easy. I was actually a bit surprised by the 40% of people that said that it would be easy, but I guess we will see. Unfortunately, I no longer have Windows on my computer, so I will do it on the VM on the cloud, but I can tell you it also works on Windows. So the title of the talk is Providing a Unified User Environment for Canada's National Advanced Computing Centers. So I am the lead of a team in ComputeCanada that has as mandate to provide the software environment for the users, but also support the tickets, the help desk, and the documentation. The two other names on the talk, Bart Oldeman is the lead for software installation. Ryan Taylor is the lead for the CVMFS infrastructure, which I will be talking about a bit later. So the outline of the presentation, I'll talk a little bit about what ComputeCanada is, what are the goals and the design that we chose for the software stack. Then I'll talk about the tools that we use, and I'll finish on talking a bit about documentation, monitoring, and do a demo. By the way, if you have questions, feel free to, I have the chat open, so feel free to ask them in the chat or unmute and ask them. So ComputeCanada, I'm assuming most people here are from the States. It's a little bit like Exceed in the States, but for Canada. We support users from all academic institutions, all research disciplines. It's free access for any researchers and at a Canadian institution. ComputeCanada is the body that coordinates the efforts at the national level. It acts with 4 regional partners, regional consortia that's written on this slide. WestGrid, which includes the 4 provinces in the West, Compute or Calcul Ontario, which is for Ontario, Calcul Quebec in Quebec, and AceNet, which is for the Maritimes provinces. There's 35 members institutions, so those are big universities across the country, about 200 technical staffs, about 15,000 users, and of course, I suppose it's the same thing on the south side of the border, but there's a lot of growth every year. So the landscape is expanding. In terms of infrastructure, we have 5 major national systems that were deployed in the past 3 years, I believe. So Arbutus, which is a cloud, which is based in Victoria, it was deployed in 2016. CEDAR, which is a general purpose cluster with an Intel OmniPath network, GPUs, Intel Haswell and Skylake CPUs. Graham in Waterloo, which is basically the twin of CEDAR, except that it uses InfiniBand instead of OmniPath. Niagara, which is a large parallel cluster, it uses a non-blocking InfiniBand across all of the system. And Beluga, which is the most recently deployed in Montreal, which is also a general purpose cluster. So total, it's about 200,000 cores, 22 petaflops, 70 or probably more by now petabytes of disk, and close to 200 petabytes of tape. So in the past, there were many more small clusters across Canada, so much smaller than those ones. Those have between 30,000 to 70,000 cores, up to 1,000 GPU. Oh, sorry, I was reading the chat. So in the past, we had many more smaller clusters. 3 years ago, our funders decided that it was time to reduce the number of clusters and make them bigger instead. And there was also a big push to make the teams, which are located in 30-something institution in Canada, so make the people collaborate much more with each other, whereas in the past, the clusters were basically managed in silo. So this is the context in which our project started. Yeah, okay, and I was explaining that, but I had a slide about that. You might have seen that cartoon, which is, yeah, so two people talk. There's a big insurance. One thinks it's about the CEO, and the other one, well, no, it's about the person who knows our build script work. So that was pretty much that way in the past. It was, and every software was installed differently on different clusters, maybe documented or not, and that had to be repeated on each cluster and for each software. So that doesn't scale, especially in the size that we are now. So the goal, we wanted to have to present to users a consistent environment, the same on all clusters. We wanted it to be easy to use and across all sides, and of course, we are doing HPC, so we wanted to fine tune it for the hardware, so to have good performance. So because we wanted the stack to be consistent, that meant a few things. One of which is that we cannot rely on the underlying operating system software stack. So our clusters currently all run CentOS 7, but there's no guarantee that one of the cluster won't upgrade to CentOS 8 before the other ones. There's no guarantee that the exact same OS packages are installed, because the clusters are still managed by different sysadmin teams. They also employ different strategies. One of them doesn't have local disks, whereas the other ones have, so that kind of dictates different strategies for the number of packages that are installed in the OS. So we cannot rely on that. Since we knew that we would have, so right now we have about 40 people across Canada that can install software and do install software on the stack. So we wanted that to be tracked, to be reproducible. So we wanted some kind of automation. And because the clusters are much larger, they serve a much wider variety of users. That means we have a much wider variety of software that is installed. We actually have close to 5,000 builds at this day, and so we needed some way to make this manageable. So not to present the users with 5,000 different options. So with that, with those requirements, we first chose a distribution mechanism, which is CVMFS. I will talk a bit more about that in the other slide. So it stands for CERN Virtual Machine File System. As the name says, it's a file system. It was designed by CERN for the Large Hadron Collider and that kind of experiment. So they run everywhere around the world. So they designed a file system that can be that can work in a geo-distributed environment, like what we have with our clusters. For consistency, we first had to have a common layer that would be independent of the OS. For that, we chose Nix. So, and I will also talk in more detail about Nix a bit later, but it provides an abstraction layer between the OS and the scientific software stack. For the scientific software stack, we chose to use EasyBuild, which is a project that originated from University of Ghent in Belgium. It's somewhat of a competitor to SPAC, which you might have heard and is used at is developed by Lawrence Livermore. But we chose EasyBuild at the time, and we'll stick with that. And for the ease of use, because of the large number of software, we definitely wanted to have a hierarchical module tree, and that was enabled by Lmod, which is developed at TAC, which some of you might know. So CVMFS, the distribution mechanism. So what it is, it's highly optimized for geodistribution. So originally for the high energy physics, the way it works is the clients mount a read-only file system via Fuse, and the data for the file system is transmitted through HTTP. So it offers transparent deduplication, chunking, and compression. You will see a bit later, we have close to 3 terabytes worth of software, but actually on the CVMFS infrastructure, it's only 600 gigabytes because of the deduplication and the compression. It's a system that works in a poll fashion, so the clients will poll the files on demand rather than pushing somewhere. So that makes it easier. We can install software even if the clusters are not up, because they will just pull what's needed when they need it. To avoid having latency issues, there is also aggressive caching. So there are multiple layers of caching to cache, to provide redundancy and minimize latency when you're accessing software. It's designed in a way that's highly reliable, so there are redundant servers. There's no single point of failure, and it transparently fails over between the different servers if one is rebooted. And finally, it provides atomic updates. So contrary, for example, to rsync, users will never see a partial software. They will either see the new software installed and they will have everything that they need for it, or they won't see it. But they won't ever be in a state that, hey, this module is there, but the software is not there, or part of the software is missing. So schematically, the way it works, we have the data entry point. So before that, we have our build infrastructure. So that's a VM in the cloud somewhere. We build the software, and then we push to the stratum 0. We have one stratum 0. If that server goes down, the only thing it means is that we cannot push new software until it's back up, but it does not fail any of the readers. That stratum 0 is completely replicated into multiple stratum 1s. We have 2 public ones and a couple private ones as well that are distributed across Canada. So this box here is managed by our CVMFS infrastructure team led by Ryan Taylor. on the site, typically what you will have, since the data is distributed by HTTP, you will have a couple of HTTP squibs, so caching proxies that will host a partial cache of what has been used on your cluster. And then the client nodes also have a local cache on disk typically, or if there is no disk on the local node, the local cache can be put on the parallel file system. We have one cluster that works that way. So when a user requests a file on a client node, it will first look whether it already has it, which typically will be the case. If not, they will go to the local squid to fetch the data. If it's not there, it will go to the Stratum 1 layer. And there it will be there because it's a complete replication. So the software design overview, we separated the types of software in a couple of layers. So first, there's the OS layer that's not managed by my team. It's the OS kernel, it's the daemons, it's anything that is privileged. It's the drivers. So those are always local. Then in the gray area, we have things like Slurm, Lustre client libraries that are needed to build, for example, OpenMPI. So we have a version that is on Nix that is distributed by the CVMFS file system, but at runtime it gets shadowed by what's installed on the cluster. We need to make sure that they're compatible, but usually it's not an issue. Then the Nix layer will include everything that you would typically have on a Linux operating system, down to the libc, the autotool, the bash, the bin utils, that will be distributed by Nix. So Nix is really good for isolating itself from the base OS. And on top of that, the scientific application layer, which includes the compilers, the high-level applications like Bromax or OpenFOAM or name it. We build for multiple different architectures. So we support SSE3 for some legacy cluster, AVX as well, AVX2 for our newer clusters, and AVX512 for the very newest cluster. So both Nix and EasyBuild, the builds are basically a recipe. So nothing can be installed on the system without writing in a recipe. So there's no manual action that you can do. So everything is scripted. We have our own fork of the repositories. So ComputeCanada is a pretty high contributor to EasyBuild these days. Bart, my colleague, is actually one of the maintainers of EasyBuild since about a year or so. Not so much with Nix. We do have some minor local modification to Nix, but we basically use it as is. But all of this is public. The recipes are on our GitHub organization. So Nix, so it's basically a package management system similar to Yum or your favorite system. The difference is that it is highly targeted at having deterministic builds. So that means you change a minor version of a dependency, everything gets rebuilt. It has, when you install something, it will always install it in a directory that is a hash of the recipe and of the dependencies. It will not overwrite anything that was installed before, so you can go back in time and you are sure that if you have the same hash, you have exactly the same build. So we use that to provide the dependencies, so glibc, libxml, the kind of thing that you would install in the OS. The exception, so the things that it does not include, as I said, the drivers, kernel modules, anything that would be privileged, it's not included by design. So everything we do here is something that a user could, a knowledgeable user could do by themselves. EasyBuild, so for the advanced research computing layer, so similar to Nix, it's a package manager. It provides automation, configuration, logging, testing of the builds. Everything is tracked in Git. It generates the module files automatically, which is pretty nice. You can build in parallel either on one node or even on a cluster. We typically don't build on a cluster, but we could. And there are thousands of community recipes, which include basically all of the applications that you might wish. I'd say 99% of the time, when we need something, there's already a recipe written for that. There are a few oddballs that we need to write one, but it's not that complicated. The typical process we use to install the packages. So even with that many people installing software, we have a lot of users and a lot of requests. So we don't install things unless it's requested by a user. So it always starts with a user request. Then the staff will decide whether it should be installed globally or in the user's account. The default route is typically globally because it's often just as hard to install it in one user's account than install it globally. So we figure we might as well install it globally. When we do that, so we have a build node, we build the package, we test it there. When I say test it, we don't have time to do detailed testing, but there is at least the tests that are automated in EasyBuild, which are sanity tests. So either running a basic command or ensuring that some files are there. If it's not okay, we rebuild it. If it's okay, we have a development CVMFS repository that can be seen on the cluster, so we can use it to test on the cluster, or we have a special test node that we can use for that. The users could have access to it, but it's not visible without us telling them to do something to have access to it. If it's all okay, then we will publish it to the production repository, and then it will become directly visible on the software on the clusters. So it gets exposed to the users just at the very last step. And since it's all tracked, and even in CVMFS, we can roll back to a previous version. So if at some point we screw up, which thankfully does not happen often, we can go back and recover the files from CVMFS. I hear someone. No? Okay. So in terms of number, so this slide, I think this slide dates from the early June this summer. So we have over 600 scientific applications with 4,000 permutations. So on this plot, the blue line here is number of software per software name. So GROMACS is 1, MD is 1. The red one, it includes different version of the same software. Purple, I'll skip over, I'll talk later about it. The orange one, it includes the tool chain. So what the tool chains are, is it built with GCC? Is it built with Intel? Which version of GCC or Intel or PGI? Is it with OpenMPI or with CUDA? So those are the tool chains. And the green line is if we include the permutation with the different architecture that we support. So you can see around the fall of last year, we had a big spike here. That was when we rebuilt the whole software stack for Beluga, the newest cluster that has AVX 512. So because of all of the automation that we have, the build time was basically limited by the CPU power we had to compile. So it took about a week to recompile 600 different software. And then there were a couple oddballs that did not compile with AVX512 for some bug in the compiler or some various reason. But the vast majority of the stack we were able to recompile in a matter of a couple of days. The plot on the bottom here, that's the space that is used on the CVMFS infrastructure. So as I said, because of the duplication, the compression, we have about 600 gigabytes used, even though the size of the software stack on the, if you were to copy all of it, it's over 3 terabytes. And the bump that happened for AVX512 is actually much smaller in size compared to the number of applications being rebuilt. That's because when we rebuild an application, there will be sources that are the same. There will be sometimes data sets in an application that are the same. So all of those are deduplicated, and there's only one copy that is kept. We also support some number of licensed package. Those are not available publicly, contrary to the open source packages, unfortunately. But we have agreements with all of these vendors. Well, either agreements or we have recipes written in EasyBuild so that users can install it in their account easily. But most of them, we have agreements with the vendors. Some are more open to distribution, others are not. So, for example, VASP is installed only on specific cluster and not on CVMFS. We have varying options here. So for the user interface, so as I said, we use Lmod with a hierarchy. So we first have quite a large number of packages that are built at what we call the core level. So that would be anything that is a binary package that we don't compile, like MATLAB or like the Intel compiler or that kind of thing, or packages that we deem are not performance critical. So those we will build for compatibility rather than performance. Then we have everything that falls under the side that we do need performance. Then we build for different CPU architectures separately, and we will have under that the compiler level of the hierarchy, compiler MPI, compiler CUDA, and the combination of compiler CUDA and MPI. So those are the levels of hierarchy that we have in our modules.
There's a question in the chat.
Yes. Okay, why we use both? Yes, good question. So Nix, there are a couple of channels that support, of Nix channels that support scientific applications. There are really not that many though. It's really targeted by the list of packages that it offers. It's really targeted to what you would install in a typical operating system. EasyBuild is, on the contrary, is really targeted at scientific software. So there's a big difference in the types of packages for which there are recipes already written for it. It's also much easier to write a recipe for EasyBuild than it is for Nix. I think there are only 2 or 3 people within ComputeCanada that have written Nix recipes, whereas over 40 of them have written a EasyBuild recipe. Does that, I hope that answers the question. We also do something a bit special with Python, and this slide, these few slides are a bit of a crack at Anaconda. I don't know if there's any Anaconda lover in the room, but so Anaconda was first, well, my understanding is that Anaconda was first designed for basically fixing a problem in Python that Python is not good at packaging. And that's all fine if it were only for Python packages. The big problem we see with Anaconda is that people can do things like that. So install GCC in Conda or OpenMPI or CUDA, and that causes a large number of problems on the system. It will duplicate software. It will typically not be software optimized for the hardware. So instead, we explicitly discourage users to use Anaconda in our documentation. Instead, what we do is we use Python wheels. So wheels are basically a binary package, such as what is offered by Yum, but for Python. And the trick is you can compile your own wheels that you will have linked against your own compiled libraries. So that's what we do. We have over 2,000 different wheels going from TensorFlow that is built for CPU or GPU to things like NumPy, which we will link against our MKL, for example, or H5, which will be linked against our HDF5 installation. And we will have declinations for the different CPU architecture as well. So this, so this quote, that's actually about the animals. So remember that Anacondas are heavier and bulkier, while Pythons are longer and more agile. But I think it applies pretty well to the two tools, Python and Anaconda. So documentation, since everything is scripted, we also have automated the generation of documentation pages. Well, not so much documentation pages as listings. So if you go on that link, for example, on the wiki of ComputeCanada, we have a page available software, which has the different architecture, and it is automatically updated when we install software to list what's available for the different architecture, and also descriptions or prerequisites that are automatically automatically generated from the help of the module files. We have the same thing for wheels. So we have automated on, there's a script that will take the wheels and update the wiki automatically. I see comment. Yeah, TensorFlow is a bit tricky. It tends to download libraries, and that might not be compatible with what you have on the system. Fortunately, we have two people that specialize in building TensorFlows for wheels. But sometimes, so for example, PyTorch, it turns out that the binary wheel, which is built by Facebook, Torch is Facebook, right? Anyway, which is built by them. It already supports multiple architecture and CPU and GPU, and will detect at runtime. So in these cases, we might just download the binary wheel that is provided. There is one case that we were not able to address with wheels, and this is KIME2, because it has a truckload of dependencies, and they explicitly don't support pip, but only conda. And for that, we are looking to use containers and deploy them as a module, a little bit like community collection. So that was an idea we got at PERC to do that, but we haven't done that yet. FastX, I don't know that one. I could check whether we have it. FastX doesn't look like it got requested yet. It doesn't look like we have a wheel for that. What about our, oh, there was a question about the wiki first. So the update, basically, we have, we have a VM that has the software stack available. We have a script in a cron tab that will just take the output from module or the list of wheel, message it a little bit, and then use the media wiki API to update the page on the cron tab. If there's been new software installed, the script will detect it and update the web page, the wiki page. What about R? We for R and for Perl, well, Perl we don't have that many, but for R, typically users can just run install.packages in R, and it works. Usually it works well. So that's the solution that we instruct users to use. Sometimes we need to fiddle a little bit with the LD library path or something like that. We need to give them more instructions, but in the vast majority of cases, install.packages works just fine. Akin to VNC server. Oh, that's the FastX. Okay. Yeah, I don't know about that software. For VNC, we do have VNC that is used on some clusters. We do have some X2Go as well that is supported on some clusters, but that varies. That's typically will be handled by the systems team. Yeah, Anaconda and their bash RC, that's another reason to tell users not to use Anaconda, because it messes their bash RC and creates issues. Yeah, I would be just happy if Anaconda disappeared, but I know that's not realistic. So we try to make the best of it with Python wheels, and most of the time it works. Okay. Yeah, the FastX. I guess we'd have to talk about that offline. I don't know it enough. So the last question, actually, I'll do better than give you a guest account. I will show you how you can use it in your own VM. So stay tuned for a little bit later on the talk. Well, actually, it's the next slide. So you can use this too. So on our wiki, accessing CVMFS, that is public. It allows you to mount the software stack with just a couple of commands. It takes minutes, and I'll do a demo about that. And we have opened that at Perk, basically. We have a couple of users that have started using that. We have one group here at my institution who mounts our software stack in their Docker, on their infrastructure, so that they can build the software and then send it to our cluster, and it just finds the library and works. So it makes it easier for their user than to use their software on the cluster. And I think that's the demo. So this is the interface for our OpenStack. So Arbutus in Victoria, and I will actually start a new VM just to show you that it's pretty quick. Hopefully nothing goes wrong in the demo, even though it's sometimes a bit kamikaze to try and do a demo here live, but it should go well.
Yeah, I think a few of us are noticing maybe your microphone moved or something. You got quiet on us.
Oh, okay. can you still hear? Or
Still quiet a little bit. We hear you, but pretty faint.
still quiet. I'll try to get closer to my mic. I don't know. Let me try something. Hello?
We heard that.
Oh, you heard that?
Yep, that's
Perfect.
better.
Okay, I'm not sure what happened. I guess it gave time for the VM to spawn. That's good. All right, so I just started a new VM that runs on the cloud somewhere in Victoria. It already has my SSH key, so I can log into it. And basically, it's a brand new CentOS 7.6 VM. There's nothing installed. Even Vim is not installed. There's no module. There's nothing. It's a brand new VM. So with the instructions on the wiki, and we have instructions for CentOS, Fedora, Debian, Ubuntu, OpenSUSE, and Windows. So for Windows, you need to have software again. I don't know how to fix that. I'll just try to speak louder, I guess. For Windows, you need to have Windows subsystem for Linux. And you need to have the version 2, which has an actual, a real Linux kernel inside of it. But so for CentOS, so I just copy a couple of lines here. So this installs the CVMFS repository and the client. So that repository is handled by CERN. This one is an RPM that we generate, and we also have Debian packages that contains the information to access our repository. And then we install the client and the setup. That will take a few seconds. So the keys are documented if you want to compare them. I know they are fine, so I will just accept them. And there is one file that needs to be edited, which is a config file, so CVMFS default .local. Oh, right, I said there's nothing installed. I'll install Vim. So there's a couple of configuration options. This is the quota limit. This is the size of the cache that you will have on the VM. And typically you would have squid proxies that you would use. So if you want to use it on a cluster, we ask that you do have a squid proxy to reduce the load on our servers. In the case of just a VM, I can just I can just access the stratum 1 directly. And I forgot sudo here. So once this file is created, there's a little way to test, to check the setup. And hopefully it will tell me that everything is okay. I can probe to see that the software is there. And finally, we have, so on our cluster, this is automatically sourced, but we have a config file, a profile file that we have for bash and for CSH. And just like that, I have access to the modules on the cluster. The first time you access the module, it might take a few seconds, but after that, it will become much quicker. So here, those are some of the modules that are there. It automatically detected that this is a node that supports AVX2. It automatically detected that this is a node that has Ethernet. It could detect InfiniBand or OmniPath, and this will change runtime variables that are used, for example, in OpenMPI. So now I can see, so there's a default Python provided by Nix, which is 2.7. In the future, it might change for Python.
Yeah, if you're speaking, we're not hearing you right now.
Can you hear me now?
Yep, you're back.
Okay. Yeah, sorry, this wireless headset seems a bit finicky. So now I loaded Python, so I have Python 3.7 that is loaded. And so the way we instruct our users to install packages is to create a virtual environment. So if I want, I can do that. And if I try to install, for example, NumPy, well, it will actually fetch the version of NumPy that we have installed in our wheel repository. So we have a bunch of different versions of NumPy. It will select the right one. If I try, not sure I will remember the command, but if I import NumPy, there's I don't remember. Is it numpy.config? I don't remember exactly, but there's a way to, yeah, it's not config. There's a way to display that it uses our MKL implementation. I just don't remember how to do it, but it does use the version of MKL that we have installed on the stack. So it will use probably version 2018, I think. It would probably be 2018.3. So you see that you can have the software stack available in your VM or your cluster in a matter of minutes. This also, as I said, works on Windows. I did that at PERC. I could open ParaView, I could open a browser. I did not set up export wording for that VM, so I cannot do that here. But if you do, you could also open it. For the module with Lmod, we also have module logging. So every time somebody loads a module, it writes a log line into the system log. So it won't send anything to ComputeCanada, but it writes it in your local system log. And then on our cluster, we take those system log and send it to an Elasticsearch stack with Grafana, so we can see which module is used on which cluster by which user. So if we ever have to deprecate a module, like we are considering, although it's not decided for Python 2.7, since Python is going to be unsupported. Python 2 is going to be unsupported starting the end of this year. So we can see who's still using Python 2, then contact them and get them to move to Python 3 or that kind of thing. So this is what it was a couple of years ago, and this is what it is these days. So it's one software stack across all of the cluster. That means user can move between cluster, basically don't have to change anything. Everything is scripted, so when we need to recompile something, it's just it's CPU bound. It's not bound by the time that we have. So that helped greatly in supporting the large number of users that we have. Any more questions? And maybe people can open their mic too. I can. I don't hear anything.
I guess I'll throw out kind of a question that builds off of something somebody put earlier. Kind of the difference of the Nix and the EasyBuild. You know, you kind of emphasized that the Nix was around a lot of the base system pieces, the
Right.
dependencies and these other things. Can you talk a little bit more about how all these cascade together, and maybe it's done at the modules, how you kind of weave all these pieces together so that you have a full stack then from the glibc all the way up to the scientific application?
Right. So, and I guess it's best to do that. With the demo. So we have a module called Nix packages that basically contains a path to bin directory, and in that bin directory, that's where all of the binaries or the commands from that you would typically get in an OS, that's where they will get linked to. So the way Nix works is all of these are actually symlinks, and this is Nix managing that. So it's symlinks to what is actually installed. So like I said before, this is in a directory that contains a hash of the recipe. So Nix install every single packages in different directory and then creates a link farm. And the way we integrate that with EasyBuild is through a module. So what users will see is really what is in what is called a Nix profile. This includes this includes the bin directory and the lib directory, and those will be where it's found. Note that we are looking to move away from Nix and use Gen2 prefix instead of that, because the hash, the concept of the hash directory, that's all very nice for reproducibility. However, there are sometimes it causes problems at some occasions So the way we build, so we have a linker wrapper, for example, that will that will set the run path into the binaries that are compiled. And what we want the linker wrapper to do for the libraries that are installed in Nix is not to link to those hashes, but to link to the profile, which is the symlink farm. And it happened that the hash directory leaked basically into the environment, and that caused issue when we did garbage collection. So Gen2 prefix doesn't have that issue and still allows to manage all of the lower level stuff. How difficult was it to create the Grafana interface? So the hardware, I know basically nothing about. This is managed by, we have a team, monitoring team at the ComputeCanada level that manages that. So I cannot answer that question. The logs, so the only part that I play in the logs is our log messages. So every time you load a module, there's a log line that is written, and it's a key value log line. And this basically, all of the syslog and the syslog of the clusters get automatically scraped and sent to ELK. I don't know the details of what's underneath. Can we extend your CVMFS? Yes, so you can definitely use your compiler. We already have EB, so EasyBuild, that is supported. We actually have some software packages, especially commercial packages, for which we don't have an agreement with the vendor, and we instead write an EasyBuild recipe that users can run, and maybe I can show that. Material Studio is one of them. So we wrote an EasyBuild recipe, and users will run EasyBuild directly in their account, and it will create a module in their account that will basically interact with our the rest of our stack. I don't know if that answered the question, but it's definitely possible to do that. No more questions? So if you want to know more, so the slides are available. The paper, I think you had it in the doc, so the paper is available. And on the the accessing CVMFS page, I will post that in your Google Doc. There is the way to contact us if you have further questions. Oh, I see another one. Recompiling for another architecture. So yeah, the AMD EPIC, well, that should support AVX2. Although when you compile with the Intel compiler, sometimes even if the instructions are compatible, it will just check and tell you, nope, this is not an Intel CPU, I don't want to run. So the way we compile stuff for different architecture, we basically use the same recipe, but we change the value of an environment variable. If I wanted to recompile OpenMPI 3.3.1.2 for Intel 2019, for example, but I want to compile it for AVX, we just specify that variable, and our scripts automatically know which compiler flag to add for that. We would have to do a little bit of tweaking for AMD EPIC, but it should not be very complicated. Do we use containers for any software? Our users do. We do support Singularity on the clusters. We don't directly, we being my team, we have considered it for some very hard software to install where there are many dependencies, but we tend to avoid containers as much as possible.
All right. So we're at the top of the hour. We really appreciate your time, Maxim, and it was an excellent presentation and talk.
Thank you.
Appreciate everybody's time today. We will go ahead and get this recording posted. And
can you send me the link to that when you post it?
Yep, we will share that out with everybody. And again, the Slack channel is available. We can follow up with any additional questions for anybody who has them. Thanks, everybody.
All right, thanks for having me. I'm not sure I caught this. All right, thanks.
Thank you.